Our next case is Dennis the Menace Veer. He's Persevere's grandson. And in previous chapters, they've already laid out this family. This poor old guy has a grandson that drives him nuts, and they nicknamed the grandson after a comic strip character, Dennis the Menace. Okay. Well, it says here that Dennis is a 3-year-old male who ingested 250 times 325 milligram tablets. That's up to, because they don't know how many he took. But he had a bottle of these 325 milligram tablets, and a full bottle holds 250 of them, and they don't know how many he took. His grandfather removed some from his mouth. He didn't know how many he swallowed, and when he arrived at the emergency room, the kid appeared bright and alert. What they did is they pumped his stomach, and they found several tablets doing that. And the next thing they did was just watched him. They measured his blood aspirin level, salicylate level, and it was 92 micrograms per milliliter, and they consider that fairly safe. They kept him overnight, just to be sure, and in the morning he was down to 24 micrograms per milliliter, and they let him go. Our objective is, it says, concerning Dennis, if the pKa for salicylic acid and acetyl salicylate, or acetyl salicylate, depending on how you pronounce this, is 3.5, is aspirin a weak or a strong acid? Which form is prevalent in the stomach at pH 1, and which form is prevalent in the blood? Okay. Prove it using the Henderson-Hasselbalch equation. The first thing we want to do is get some idea of what aspirin looks like here. Zoom this up. Okay. Okay. This is acetyl salicylate. To a lot of people and to a chemist, it's usually acetyl salicylate. That's this part without the proton. If you put the proton on here, it's acetyl salicylic acid. Acetyl salicylic acid, or acetyl salicylic acid. And whichever one you choose to use is all right with me. I don't know which one's prevalent out there. I've heard people use both of them on several continents, so I don't think it really matters that much. It dissociates, the acid dissociates in the proton and the conjugate base. And something you don't have to know for this course right now, but you might come in handy later on, is this thing here. This is the acetyl group here, from here over, this C double bond O and this CH3. That's the acetyl group. This is an ester bond here. When you hydrolyze that, you've got a hydroxide there and acetic acid here on this side. When this thing goes into your bloodstream, this happens very quickly. It goes into cells, and this happens very quickly. And in fact, one of the principal reactions of this compound is to transfer this acetyl group to enzyme active sites and things like that, and it changes metabolism quite dramatically. In the bloodstream, though, once you take this compound, once it gets in the bloodstream, very quickly, most of this is converted to salicylate, salicylic acid, or you could call it salicylate, because it's going to be, if the pKa is around 3, we're going to prove to you right now that it's dissociated in the bloodstream. I'll try to blow this up a little bit. This top reaction up here gives you the acetyl salicylic acid to acetyl salicylate plus a proton. It tells you the pKa is 3.5. The minute you see that, you say, oh, a weak acid. I could use the Henderson-Hasselbalch equation to answer probably anything this guy's going to ask me. So the minute you see that weak acid, you say it's a buffer. I can predict whether it's going to be in the acid form or the conjugate base form, which we also call the salt form. I can predict that. You just tell me the pH. I can handle that because I know how to set up this Henderson-Hasselbalch equation here to say pH equals pKa plus a log of the salt over the acid. Now I'm going to blow this up a little more so maybe you can see it from your chair there. Okay. All right. In the stomach, the pH is 1. So we set the equation up. We say the pH is 1. The pKa is a constant. It's 3.5. Equals a log of the salt over the acid. So without even working out the math, we say, okay, this has to be a negative value because we're going to have to subtract this from 3.5 to get 1. This is going to be equal to 2.5. And it's going to be negative. So in the stomach, I'm going to have a lot more of the denominator, the acid. And that makes sense. At the pKa, you have exactly the same amount. Let me bring that top part back down here again so I can go through this. When the pH of a solution is 3.5, you have exactly the same amount of the acid and the salt. Now, what is going to happen if all of a sudden we add a lot more acid to lower the pH of the solution? Well, it's going to drive this reaction in this direction, and you're going to get a lot more of the acid form. And I can solve the blood pH for you right away, too, because I'm going to say if we start out equal, at pH of 3.5, we have an equal amount. Well, if I take away a bunch of protons, which I have to do to get to pH 7, I'm going to move this reaction in that direction. I'm going to have a lot more of the salt. But let's go back and prove it. Let's go back here and prove it. Okay. We set this up and we say the pH is 1, the pKa is 3.5. We move the 3.5 to this side of the equation. We get 2.5. But we got a minus sign there, and that bothers us. How are we going to get rid of the minus sign? We multiply both sides by a -1, and then we turn the minus log we get into a plus by inverting the denominator and the numerator. And here we've done that. The numerator here was acetyl salicylate, and here it's acetyl salicylic acid. And the minute you look at this, you say 2.5, well, that's between 2 and 3. If this is 2, this value has to be 100. If this is 3, this value has to be 1,000. So somewheres, we know that this ratio is somewheres between 100 and 1,000. So right away, I can tell you I have a lot more of this acid. But we'll solve it. When we solve it, it turns out that there's 316 molecules of the acid for every molecule of the salt in the stomach at pH 1. But in a while you'll learn, you may come to the place in your life where you'll say, if I know the pKa and I know the acid, and I know I'm 2 or 3 points below there, I've got at least 1,000 to 1 here. Or if I'm 2 points below, I got at least 100 to 1 here. You won't even have to go through equation. You'll just look at it and say, I got a lot more of this than that. Okay, in the blood it's 7.4. In the blood, the pH is 7.4. So we set the equation up again. The equation is the pH equals the pKa plus the log of the salt over the acid. We move the 3.5 to this side, and it turns out to be 3.9. This is between 3 and 4. So we know it's between 1,000 and 10,000, this ratio here. And sure enough, when we solve for the anti-log, we put up 10 to the 3.9 is equal to 7,900. That's the ratio of the salt to the acid. So above the pH, when we have the pH substantially above the pKa, as we do in the blood, we have mostly the salt of the acid. And when we have a pH substantially below the pKa, which we do in the stomach, we have mostly the acid form. Let's see if that, okay. So we get back to the objective. It says, concerning Dennis Veer, if the pKa for acetyl salicylic acid and acetyl salicylate is 3.5. Is aspirin a weak or a strong acid? The minute we saw the pKa, we said weak acid. His grandfather removed some, which form is prevalent in the stomach? Well, we figured that out. Which form is present in the blood? We figured that out. The salt's present in the blood, the acid form's present in the stomach, and we did it using the Henderson-Hasselbalch equation. So we've completed that objective, and all the other stuff about aspirin that's interesting, we don't study that. That's not on the exam. The objective is what is going to be questioned.